All right, hi everybody. Welcome to week 2. So we'll basically sort of continue from where we left off last week, introduce a few more concepts. I've sort of given myself a template here to work with to stay on track. The first thing I want to discuss is conditional logic. And conditional logic refers to tools and methods which allow you to control the flow of information in a program. And there's a reference file called control structures. And the control structures file just kind of outlines the some of the basic control structures. So it refers to things like if, if, then, else. This also refers to while loops, for, and methods like this. And these are pretty ubiquitous concepts. They show up in just about every language. They're pretty essential tools because when you're defining a function that has some behavior, there are many situations where you want the program to behave differently based on the input. And just as a very basic example, imagine you are you have a MIDI keyboard connected to SuperCollider, and you're playing some melody, and you want to say, okay, when the performer plays a note number that is below 40 or something, I'd like that to be a trigger that causes something else to happen. So you have this sort of interactivity, and so the program is constantly checking on every note. Does this note meet the condition? No. Okay. Does it meet the condition? No. Finally, does it meet the condition? Yes. Okay. We branch off into a different part of the program. And so I'm just going to show if, and I'll let you sort of study this file and look at the examples here for while and for. So an if looks like this. We're just going to make a little chunk of code here. The structure, there's a couple different syntactical ways to write this, but the way that I first learned and the way that I tend to do it is by putting the if and then opening the parentheses. And there are 3 things we need here. We need the conditional expression, some expression that returns a Boolean value. And a Boolean value refers to there's 2 types, true and false. And so there are a couple of ways, there's a couple of different expressions. For example, we want to know, is some value equal to some other value? And we do this with the double equals. So this is basically an equal sign with a question mark on top of it, like is 2 equal to 3? And that's false. And 2, of course, is equal to 2. That is true. For negation, we use exclamation point equals. And what this means is not equal to. So is 2 not equal to 2? That's false, right? Is 2 not equal to 3? That is true. And then there's the usual greater than and less than. Right? So is 2 greater than 3? That's false. 2 less than 3? That's true. And then for the binary operators, conditional operators that are greater than or equal to, greater than, or less than or equal to, that is it looks like this. 2 less than or equal to 3 is true. 2 greater than or equal to 3, false. Right? And so if these are equal, these 2 values on either side, then this one here is true, right? Because it has to be greater than or equal to. And this one is false. So some sort of expression here. We'll go ahead and say we'll take the array 0, 1, and we're going to apply the choose method, which is just going to randomly pick one of these 2 items. And actually, the semicolon is wrong. We need a comma here. And then two functions, again, separated by commas. And the first function is evaluated if the condition is true. The second is evaluated if the condition is false. So here we might say 0 was chosen. And here we might say, we are not done here. I'm skipping around quite a bit. This is not a Boolean value, right? We're going to have to do something like equals 0. My mistake. Okay, so here we have a complete if construction. So if we evaluate this, we see 1 was chosen. And this is a very useless thing to do, what we're doing, right? We're not doing anything of consequence here. It's a very pure and simple demonstration. But we could, it's pretty easy to imagine some sort of other situation where the contents of these functions actually do something relevant, like making a sound, updating some parameter of some sound. We might, at some point in the future, have a process which is looping and repeatedly asking this question, repeatedly checking some value and saying, you know, is now is the condition met, now is the condition met, and so forth. And before we wrap up here, let's just try to connect these conditional concepts to what we already know about functions. So we'll build a function here, and we'll put a conditional statement inside of our if based on the input. So if the input is greater than 5, then we'll, as a placeholder, just because we haven't booted the server yet, we'll just imagine that we play a sine wave or something, right? And if it's not greater than 5, we play some noise. All right, so just taking a step back, we've got a function named tilde_func. It takes one input, and it then evaluates a conditional statement. It says, okay, if this is bigger than 5, I'm going to do this first function. And otherwise, I'm going to do this second function. And that's it. We've defined our function. So we can now say function.value 8. And that triggers the sine condition. 3 triggers the noise condition. What's it going to do if we just say 5? Should be noise, and it is, right? Because if input is 5, this is false, right? 5 is not greater than 5. Right. And so there are lots of other control structures here. In some situations, you may find yourself creating what are called nested ifs, and that means you sort of, within the first function, you actually nest another if statement. So it's sort of a multi-branching operation, a tree with several branches. You take one path, and then you've come to yet another fork in the road. You have to check another condition, and then you go both ways. And nested ifs get pretty obnoxious and ugly after a few nests, and there are alternatives, particularly case and switch. I prefer case, which is here. And I think I'll do a quick example here. This is not quite the syntax I use. It's both a blessing and a curse that there are so many syntax varieties in SuperCollider. But let's look at a case really quickly. I'm just going to copy this function. case allows you to specify an arbitrary number of conditions, and the first one in the sequential order in which they appear, that is true. That tells it which function to evaluate. So instead of an if here, we say case, and then we just provide pairs of functions and basically conditional checks, and then actions to be taken. So we'll say input less than 0. That'll be our sign. If input is greater than 10, that'll be noise. And you know, if for example you're at the end and all your conditions have been exhausted, and if all of them are false, there's only one thing left to do. It's this last thing. So I will sometimes just put the word true in here to guarantee that at least one of these is going to be true. And here we'll say, I don't know, sawtooth. .postln. The commas are not necessary in this particular case, but we do need a semicolon at the end. And I believe you can hold Shift and press Tab to tab align these if you are into that sort of thing. All right, so now if we say -2000, that's going to be signed because it triggers the first condition. It runs into this one and says, oh, that's definitely true, and so it just ignores all of this stuff. It just drops right out of the case statement, and we're finished. +2000 gives us noise, and something in between these two values, sawtooth. Right? And again, just to reinforce this, if we say 10, what are we going to see in the post window? Which one? Is it sine, noise, or sawtooth? So if it's sine, the question is 10 less than 0?
Should be sawtooth.
Correct, sawtooth, that's right. Right, because both of these are false if the value of input is 10. Okay, so good idea to get comfortable with if in particular. It's good to know case as well, because these are things that do come up quite a bit once you start building complex sort of sound programs. Playing music involves making choices, and sometimes certain conditions are met, and that causes some musical change. Okay, quick discussion about randomness. There is a help file called Randomness, which outlines a variety of random methods and classes. Computers are quite good at behaving randomly, even though technically speaking, it's not random at all. It's a very complex deterministic algorithm, which is complex enough to make us humans think, oh yeah, wow, that's pretty random, right? So we just can't see the algorithm. But if it feels random, it's good enough for us. There are really only two methods that I use for randomness. There are more, but I find that these two meet my needs most of the time. And the first one is rrand, which stands for ranged random. And it takes two values, and it will return a random value between these two. I believe it's inclusive. I think we can just say between 10 and 11. Right, so it's inclusive, including the minimum and maximum. And every time we run this, we just get a new random number. You can, as long as the first number is smaller than the next number, that's perfectly valid. Negative numbers are fine. I think even if you get very silly and like switch these, it's smart enough to invert them for you. So, and just as a reminder, I believe in one of the homework questions from last week, I talked about receiver notation and function call notation, these two different ways of expressing code. And we're used to seeing things like 3.squared, which is receiver method, receiver notation, and then the function call would be squared parentheses 3. And I'm just sort of in the habit of, I just have this knee-jerk reaction to for certain methods, I tend towards function call, and others I tend towards receiver. So this here could be rewritten as -10.rrand20, right? Where -10 is the receiver, and then it takes an additional argument which specifies the other boundary. I like the look of this better for randomness because you can very clearly see the minimum and the maximum, whereas something like this, is preferable because it reads like English. What is 3 squared, right? As opposed to squared 3. It's just really a matter of preference. It's not too important. But the main takeaway from RRAND is that it's a uniform distribution. So every possible value is equally likely. That's what we mean by the uniform distribution. And the other main thing about RRAND is that if its boundaries are integers, the result will be an integer. If either of its boundaries is a float, then the result will be a float. So if we say minus 10 to 20, the float 20, 20.0, now all of a sudden we're going to get this much finer granularity of values. And sometimes you want integers and sometimes you want floats. So just be aware. The other random method I like to use is exprand, which is almost the same thing, except it provides an exponential distribution. And in practical terms, this means the values that it outputs will gravitate towards the lower boundary. This is particularly useful for all sorts of musical parameters of which we have a logarithmic perception, like amplitude and frequency. So when we double the amplitude of some signal, we perceive a linear change in loudness. I think it's pretty much everyone's experience. And when we double the frequency of a pitch, we experience when we double the frequency of some sound, some periodic wave, we experience a linear increase in pitch. Right? We go up by octaves. The frequency is doubling each time, but we see and hear that as linear. So in those cases, it's actually quite nice to use an exponential distribution because the result tends to sound more uniform. So if we say from 1 to 100, we're going to get values which are going to be closer to 1 on average. Every now and then we get some high ones, but you can imagine a sort of exponential curve governing the distribution of random values. Exprand always outputs floats, no matter what its input arguments are. Always floats. We can round them if we like to get integers. Another option is as integer, which will actually convert them from the class float to the class integer. Either of these are fine. The main thing to keep in mind with exprand is that the minimum and maximum must have the same sign. In other words, the range cannot include or cross 0. If you do, you will, well, depending on the context, strange things will happen. In this case, we just get non, N-A-N. Does anyone know what non is short for? Not a number. Right. It's a special value, which is not a number. So this is pretty harmless here, but most of the time in a synthesis context, if you include some sort of exponential number generator and you accidentally cross 0 with the boundaries, I'd say 80% of the time what happens is you just get silence. You might sometimes get a big click at the beginning and then nothing else. Very rarely will it sort of blow up on you violently. But if you just keep in mind that you can't cross 0, then you'll be in pretty good shape. Right? You can also do something like this. Right? This is perfectly fine. An alternative, also and remember, if you switch these values, if you want to just type it like this is also fine. It's gonna invert these values, and again, they gravitate towards the lower boundary, regardless, I think. Yeah, regardless of, well, now I'm not so sure. Okay, yeah, I think it's, even if you switch the minimum and maximum, it corrects them for you. And, you know, frankly, I've never actually thought about this. I would imagine they sort of more accurately than saying the numbers gravitate towards the lower bound would be to say they gravitate towards 0. I think that's what happens here. Of course, if you want negative numbers, you can always just do this. You can use the method neg, and that'll just take the output and then flip the sign. Okay, so That's basically it, rrand and xparand. And if you want more, you can take a look at some of the other methods that are in the randomness file. So let's get back to the audio server and making some sound. And so just as a reminder, s.boot, this is the line of code which, when evaluated, tells the audio server program to awaken and lets us start manipulating sound. And I've just pulled our very simple example of a UGen function from last week. So we have a function. Here are our curly braces. We use our pipes to declare an argument. As a reminder, we can also use the arg expression to do the same thing. And then the output of this function is a sine wave with that frequency. It has an initial phase of 0, a mul value of 0.2, and an add value of 0. And if you ever want to bring up the little pop-up text that reminds you what the names are and what the default values are, you can see it's not here, but if you just click inside of these parentheses, I believe the keyboard shortcut is Shift-Command Spacebar, and that should pop it back up. Yeah?
I know on Windows, like Control Comma is the same thing, I think.
Control Comma. I wonder if that works for Mac. No, that's preferences. But yeah, if Windows, if it's Control Comma, that works, then great. I think you can also just look it up in the preferences dialog and customize it if you wish. But another way to do it is just delete and retype the left parenthesis. But that's kind of stupid. Prefer the keyboard shortcut. So we can create this function. We've defined some process that generates a signal. And we can create it by sending that function the play message and then optionally passing in custom values for any of the arguments that we've declared. So here we say, for the arguments, I'd like freak to be 400. And it starts playing. And we can use a set message by talking to the actual process that results when we play it. And then we can set, basically update any of those frequencies like this. You can bring it down to 200. And then the free message is for removing it from existence. It's a hard stop, and it destroys the corresponding process. And so if we're gonna kind of build outward from here, adding a few more features and so forth. But these are kind of the essential interactions: creating sound, manipulating sound, and stopping sound. Right? And just a few basic steps, but from this, many interesting combinations arise. It's very important to make a distinction between the process that defines the algorithm and the actual process that represents a live execution of that algorithm. So in this case, my sound is a function which represents some signal, some output. But X is the actualization of that process. And it's actually an object called a synth. We'll talk about synths next week, I think. But for now, it suffices to, it's sufficient to understand that a synth is a sound-producing or sound-calculating unit which lives on the audio server. And that is the object that is supposed to receive set messages and free messages. It doesn't make any sense to set or free my sound. It doesn't know how to respond to those messages because it's not the actual sound itself. So that's a common source of confusion, so it's important to make that distinction. Okay, SuperCollider is a code-based language, and that can be kind of a frustrating experience, especially if you're new, because everything feels invisible. Right? You're just working with code, you're making sound. Sometimes the sound comes out, sometimes it doesn't sound the way you want it to. So there are a half dozen or so utilities that come built in with SuperCollider that provide a graphical tool to help you debug and understand behaviors of signal generators and figure out why things aren't working. And so I'd like to go over those now. The first is is it's a method called plot, and it returns a class called a plotter. And this is just a very simple way of visualizing a specific fixed time segment of some output. So we're going to define this function, and we're just going to plot some number of seconds of it. We'll say 0.03 seconds, 30 milliseconds. That didn't work. Why didn't that work? Hold on. If we do it this way? Oh, I know why it didn't work. I figured it out. Does anyone else know why it didn't work? Let me ask the question a different way. What's the frequency of the sine wave? Doesn't have a value. Right, yeah, down here, we said, by the way, frequency doesn't have a value yet, so let's give it 400. So this is a different topic, but related here. It's always a good idea to give your declared arguments a sensible default value for cases when you try to evaluate the function and maybe forget to give it a value, like I just did. Right? So there we go. Now, if we try to now we can actually play this function, and we don't have to worry about specifying an argument if we're happy with the default. We can just say mySound.play. Right? So that's fine. So that was something I probably should have done earlier, to actually give it a default value. OK, so now we can actually go back and plot it. Aha, that looks much better. So we can resize this plot however we wish. I think if you tap the M key on your keyboard, it'll go rotate through sort of different display modes. This is sometimes useful depending on the kind of signal you're plotting. And we can see that it's a sine wave. It's got some frequency. We know it to be 400. We can also see what the MUL value does, because the sort of on the ends here, we can see the amplitude ranges from minus 0.2 to positive 0.2. And so here, this is a great way to, let's plot a little bit less of it so we can actually sort of see it. Maybe it's a little bit nicer. It's a great way to understand exactly what the arguments of a unit generator do and how they behave. So we can, for example, say plot this, and then actually change this to be something like 700, and plot that. And you can see exactly what happens here. The frequency increases. Right? And so you might, the concept of MUL also might be one to mess around with. So here's 0.2, and here's 0.8. It's going to look, let me get rid of these. It's going to look kind of the same, but if you actually look at the, here's the first one with 0.2, and this one is actually much higher, 0.8. Right? Here's this. And if we add a value of 0.3, again, it's by default, it doesn't do an excellent job of showing you what's going on. But what has happened is every value has been added to 0.3. Or maybe it makes more sense to say a 0.3 has been added to every value. So it's actually up here ranging from positive 0.1 to positive 0.5, I believe. Right? So now the center of this sine wave, the midpoint, is at 0.3. Right? So plot is very useful. It's you can imagine, if you're dealing with a UGen you've never seen before, and some arguments that don't make sense, you can just kind of create a function with the default values, that come with the UGen, and then just plot a few milliseconds or so, and then see what happens as you change them. Any sound function will respond to plot. Okay, so that's the plotter, and a lot of the tools I'm going to talk about now, they have keyboard shortcuts, and also they're available up here in the server drop-down menu. So one of them is the server meters, which is Command M or Control M. And this is just very nice, because if you're playing some sound function and you think you're supposed to be hearing something, but you don't hear something, the first thing I do is check the meters. Right? Because if I think I'm supposed to be hearing something and I see nothing on these meters, I know it's a problem with the code. Because if the code is not working, and so actually nothing is actually leaving SuperCollider. But if I run some code and I don't hear sound, but I see a big green or yellow bar here, I know SuperCollider is making sound. Right? And so it's probably something like with my mixer, with my speakers are not on or something like that. So basically we come down here, we'll go ahead and play this again, and we see it's a nice level. We can see how loud it is, things like that. So there's S dot. You can use Command M. You can use the drop-down menu. You can also say S dot meter, and that brings up the meters as well. S dot scope or show scope. We have a little waveform scope, which is very nice, very helpful. I usually like to adjust the the horizontal zoom so that it's easier to see a periodic waveform, but very nice tool. There's also the freak scope. This is a spectrum analyzer. And we can see we have a sine wave at 400 hertz right here. Just different ways of visualizing your sound, all very useful tools. And I think the last one I want to talk about is a sort of built-in volume master fader gain slider, and that is s.volume.GUI. And that should make a little window pop up. And this is just a big master fader for everything that comes out of SuperCollider. And if you adjust this fader, you should also see in the very bottom right corner of the IDE that there's some process at the end of everything, right before the signal leaves your computer. And so this is a semi-permanent thing. Even if we close this, everything now on my computer is going to be about 24 decibels quieter than it normally would. And this can get kind of confusing if you maybe adjust your volume slider and then forget about it for a while. So you can always bring it back up with s.volume.GUI and then just type 0 straight into the text window. But sometimes if you're working and it's just nice to have this handy, just in case you want to turn things down and then turn things back up. Maybe to take a phone call or have a conversation with somebody. Who knows, right? All very useful tools. Any questions so far? A few additional tools worth mentioning. Show node tree. This is a graphical representation of all of the processes that are currently alive and running on the server. Right now there's nothing. But if I play this sound, then all of a sudden we have a little white rectangle. And so this white rectangle represents a synth. It's got some number, some temporary name. We don't know anything about it other than the fact that it exists right now. But it's good to know that we have something here. And if we free that sound, it disappears. Again, this is a place to look if you think you're supposed to be hearing sound but you don't hear anything. If you're trying to make sound, there's definitely going to be a little white rectangle. There should be a white rectangle here. And if you don't see one, it means there's something wrong with your code and the synth process is not actually being created for some reason. And yeah, I think that's about it. As far as useful tools to keep in mind. Right, so the plotter, server meters, the waveform scope, the frequency analyzer, the node tree, and the volume slider. Just good workflow things. Let's now turn our attention to this UGen function, and let's just kind of expand out a little bit and diversify and make it a little more interesting. On the course website, I've uploaded a SuperCollider code file, which is basically just a list of what I've arbitrarily selected and designated as essential UGens. Because when you're new to a platform like this, you want to make certain types of sounds. You know, in theory, the kinds of generators you'll need, but you might not know exactly what they're called or where to look for them. So if I talk about a sawtooth wave or a pulse wave or white noise or a certain type of filter, those are all listed on that list, and they're worth checking out. And you can look them up in the help browser. As a reminder, Shift-Command-D will bring up a little search bar, and you can type the name of one of the UGens on that list, and you'll be able to see its arguments and some examples for how it's used. So the first thing you might notice, and maybe you have already noticed this, is that the sound is monophonic. It is only coming out of the left speaker, and there's only so much time that can pass before that becomes unbearably annoying. Right? Nobody wants to listen to only one speaker producing a sound for too long. And the default behavior of just about every unit generator is to process and or output a one-channel signal. And this is just for uniformity of behavior, because it would be kind of complicated and annoying if some unit generators outputted stereo by default and some were mono and some were quadraphonic. It would be complicated to deal with and interconnect. So they're all monophonic for the sake of simplicity. So the most obvious question is, how do we just get it to come out of both speakers? What if I want, I want to copy this sine wave and send it out of the other speaker, or put another way, I want a stereophonic sine wave, which is the same in both channels. So you might remember we talked about arrays last week. And the array is a class which is an ordered collection designated with square brackets and items separated by commas. They have a size, they have an order, and it's useful for storing data. In the context of the audio server, the audio server interprets an array containing signals, more than one signal, as a multi-channel signal. And it will attempt to route each of the signals in that array to discrete outputs. So if we have a sound and we'll declare a variable, and we'll call that sig, and say sig is equal to this sine wave. And then at the bottom here, if we say sig comma sig, what this is going to do is say, okay, we have a variable. It is a sine wave, a monophonic sine wave. And remember, these UGen functions will try to play the last code expression that it contains. And so this is an array of size 2 containing a copy of the same thing. And so we'll get one sine wave to the left and one to the right. And it's going to look like this and sound like this.
So the sig, comma sig will make the sound from the mono to the stereo?
Yeah, this construction here, the array sig comma sig, tells my sound what its final output should be, and it's an array, and the server interprets an array as a multi-channel signal. So just a few variations on this idea to really hammer home sort of what's going on. And I'm gonna get a little quicker here. I'm just, instead of renaming the function and playing it separately, I'm just going to make one function that ends with dot play, and we'll get rid of this for a second. So if we have pink noise, and we say sig comma sig, we're going to get pink noise out of both speakers. If I say, if the array is sig comma 0, we'll hear sig in the left and nothing in the right. And we can reverse this. Yeah? So there's a couple of shortcuts for arrays. I mean, imagine, you certainly wouldn't want to, a really slow way of doing this would be, or a really maybe ugly way of doing this is something like, this. Right? Actually typing out the same thing twice. Right? This is part of the reason why we like to make a variable. So we make it once, and then we can reuse it with fewer characters. So there are a couple of shortcuts for arrays which are useful to keep in mind. So if we have the number 7, right, we can say .dupe and then some number of duplications, and it returns an array containing that many copies. So 7.dupe5 gives us 5 sevens. Right? So sig.dupe2, that creates an array. And what you have to keep in mind here is that at this point in the last lines, sig is actually an array, even though there are no square brackets at all in here. It's a shortcut which creates an array. So you have to sort of visualize sig as being an array of 2 things. And then as a shortcut for this, instead of .dupe, you can just use the exclamation point. So 7 exclamation point 5 gives us an array containing 5 sevens. And so this here could just be replaced with exclamation point 2. And that also works. And this brings us to a very important and unique feature of SuperCollider called multi-channel expansion. So instead of just duplicating the unit generator, it's possible to just duplicate one of its arguments. And it looks a little bit different. It's not quite the same operation. But what happens here is, pink noise needs for its first argument a mull value. And a value of 1 would be kind of loud. So that's why I'm using 0.2, because I'd like to scale down the amplitude a little bit. But I'm actually providing the array, 0.2, 0.2. And so pink noise says, this is an array. And then multi-channel expansion kicks in. And so what happens is this pink noise becomes an array of 2 pink noises, and the amplitude values are distributed to each copy. So this ends up being an array containing 2 pink noises, but it takes less work to write it. If I were to give this something like this, what can we expect in this case? Right, first channel is going to be louder than the second. And if we reverse it, it moves over to the other side. And a sort of subtle difference here. In the case of, let's compare this to this. Right? Subtle difference here. Here we create a copy of the 0.2, and multi-channel expansion generates 2 pink noise generators. Here we just generate a monophonic pink noise generator and then copy that. And the results are actually not quite the same. So this second version here, you can see that the signals are exactly the same on these 2 channels. Here, they're unique. And the reason that happens is because here, because the array is inside, multi-channel expansion causes the unique generation of one pink noise and a new separate pink noise. And they each get the same amplitude, but they are different generators. And pink noise is a random signal, so they're both going to be unique. Here we just generate one pink noise and copy that generator, right? And so we get 2 copies of the same one. And this only comes into play with stochastic random generators. If we did this with a sine wave, these 2 examples would be exactly the same because a sine wave is completely deterministic. So, just a minor thing to keep in mind there. Okay. Let's go back to this example here and just do some basic signal manipulation here. So we have a frequency argument, we have some signal, and we're going to output a stereo version of it. So these unit generators, they represent calculations with signals. Some of them are generative, some of them process a signal. And let's just quickly unpack what a digital signal actually is. So I'm just going to generate a sine wave here. And this is true of all digital audio software. if we just sort of zoom in far enough, a digital signal is just a sequence of numbers. We call these numbers samples, but really they are just numbers. And in most cases, they are conceptualized as ranging from -1 to +1. So here we have a sine wave with an amplitude of 0.5. And so really, these are just numbers that happen to form the shape of a sine wave. And because they're just numbers, we're allowed to do any sort of mathematical operation we like. So we could add another sine wave, maybe with a frequency 1.5 times higher than our base frequency. And this is perfectly fine. Right? Or maybe just very slightly higher. And just take a moment to conceptualize what this operation actually means here. We have two sine waves, and we're adding them together. And so what we're actually doing is just taking every pair of corresponding samples and adding those together. So if we had, another sine wave below here, you can just imagine it with a different frequency, different amplitude, or maybe not a sine wave at all, just some noise generator, right? They have a pair of corresponding samples, one here and then one right below it, and those values just get added together. We get a new wave and a new sound, sometimes drastically different, sometimes not so drastically different. So we can add signals together, and when we do, it's you have to remember that when you add lots and lots of signals, depending on how they're correlated they are and phase relationships, you might end up with a signal which is drastically quite a bit louder than any individual signal. So it's usually a good idea to, scale. Like if I was just using the default mul value of 1 for both of these, and since that is the default, we could just as easily write it like this. And so adding two full amplitude sine waves together, that's going to make a sine wave which at times might actually exceed our maximum allowable level here. So it's always a good idea to do something like this at some point. Right? If I didn't do this step, it would be quite a bit louder, right? So we always have to be careful that we don't exceed 0 dB. And this is another good reason to have the meters open, is so you can actually watch the signal you're creating. And if it hits 0, it turns red, and you say, OK, something's wrong. So you've got to go in here and scale things down. Now, I think it's perfectly fine to just work around with a scaling value of like 0.1 or 0.2. That corresponds to somewhere around minus 25, minus 20 decibels, and that's still, that's still plenty loud, right? So, and here, when we take a signal and multiply it by some constant value, that is equivalent to taking that constant value and multiplying it by every single signal, right? So everything gets uniformly multiplied by this one value. All right, let's look at an example of signal modulation here. So we have a sine. Let's do something different. Let's do white noise with low amplitude. And if we just play this, we'll just hear white noise in both channels. And let's say we want to create some modulator. So this might be like a tremolo effect. I guess it's not tremolo if we're not dealing with pitched. But let's just say, let's just make a sine wave here. And we'll have it run at 2 hertz, 1 hertz. And we're going to say sig equals sig times mod. So we have our source signal, a modulator signal. We multiply them together, and then take a copy of that monophonic result and make it into a 2-channel signal. What's this going to sound like?
I think it'll be the white noise getting louder and softer.
Yeah, getting louder and softer. Right. And we have this very slow-moving sine wave, just 1 cycle per second. So up and down, and it's actually, we've got a positive and a negative region, right? And so we're multiplying the white noise by some positive value for half a second, and then negative value. It's a lot of times with these modulators, you actually want to specify a custom range, right? By default, a sine wave generates samples that are between -1 and +1. That might not be what we want in this case. We might want this to go from 0.1 to 0.6 or something like that, right? So instead of having to go in here and do the mental math of how much should we multiply and add to this signal in order to get the right range, you can just forget about mull and add entirely and tack on a range method and say, I'd like this to go from 0.1 to 0.6. So now over 1 second, it goes from 0.1 to 0.6 and back to 0.1. And we can slow this down even more. Like a day at the beach. Right? Very basic example of modulation. If we swap this out for something else like LF pulse, this is a low frequency pulse wave. And so pulse waves have just basically two states, on and off. So if we set this to be something like 4 hertz, it should pulse on and off between 0.1 and 0.6 4 times a second. 8. And yeah, so here the homework for this week is going to, at least part of it is going to focus on you building these little unit generator functions. Sometimes I'll just give you kind of an abstract idea, like make a triangle wave that does this sort of thing. And for a couple of them, I'll give you an actual sound from real life, and I'll give you some information about that. And I want you to use synthesis and modulation techniques to try to reconstruct that sound. And most of them are pretty simple, but some of them will probably make you stop and think about it a little bit. But it all boils down to just crafting a UGen function and declaring some variables, giving some things some names, and then just interconnecting those signals using the appropriate mathematical operations to get the result. And one last useful server utility before we go. We talked about like the meters and the scope and the free scope. You can also just call .pole on any unit generator. And this has the effect of printing the output in the post window. Let's actually go back to SINOSC here. Yeah. So this is particularly useful for low frequency signals. Now we can very clearly see what kind of numbers are coming out of this signal. And they directly correlate to the amplitude, basically. And right, that's sort of everything. So I think we're going to stop here. And I'll issue another problem set later in the evening. And that'll be due in a week. Yeah, I will see you all next week. You can feel free to stick around if you have questions.